morning, my dear students. This is K.P.T. Vijaya Bhaskar, lecturer in chemistry, K.B.N college, Vijayawada. Today I am going to explain you about gaseous state. It is in our first semester Unit-3 chapter. First of all, let's start the lesson with some basic concepts. Usually, matter can be exist in three states: solid state, liquid state and gaseous states. These three states are collectively called states of matter. One substance can exist in one state at room temperature, but the other two states are available at different temperatures. Say for example, water, it can exist as liquid at room temperature, but it exists as gas and solid above 100 degrees centigrade and below 0 degrees centigrade. That means if water is converted into gas above 100 degrees centigrade but below 0 degrees centigrade, it can transform to solid material, that is ice form. In certain cases, there will be a direct transformation of solid into gaseous state without obtaining liquid state. This is called sublimation. So in this case, the solid can be a direct transformed to gas. Say for example, camphor and naphthalene. The next concept is the ideal or perfect gas equation. Let's start with what are perfect gases. See, the gases which obey the gas laws such as Boyle's law, Charles' law, Avogadro's laws at all ranges of temperatures and pressures are called ideal gas or perfect gas. The molecules of these gases occupy negligible volume or no volume. So they have no intermolecular forces of attractions. So it was found that none of the known gas obey all gas laws of all temperatures and pressures. So no gas is in nature an ideal gas. Hence, the concept of ideal gas is only theoretical or hypothetical knowledge. The gas which does not obey the gas laws at all ranges of temperatures and pressure is known as non-ideal gases, or it can also called real gases. The ideal gases equation is derived from combining Boyle's law, Charles' law and Avogadro law. Let's see what are gas laws. So the first of all, Boyle's law. At constant pressure, the volume of gas is inversely proportional to its pressure. It can be expressed V is inversely proportional to P at constant temperature. The second law is Charles' law. According to Charles, at constant pressure, the volume of gas is directly proportional to its absolute temperature. So it can be expressed as V is directly proportional to T, where T is absolute temperature. The third one is Avogadro's law. At constant temperature and pressure, equal volumes of gases contain equal number of molecules. So according to this law, we can express the volume is directly proportional to N, where N means number of molecules of the gases at constant temperature and pressure. So, by combining the above three laws, we have V is proportional to 1 by P into T into N. It can be also written as V is equal to RTN by P, where R is the constant It is called molar gas constant. It has the following values: 0.0821 liters atmosphere moles inverse degrees inverse, or it can also be expressed 8.314 into 10 power 7x moles inverse degrees inverse. So from the above said laws, we have PV is equal to nRT. Here N means for N moles, or it can be also written as PV is equal to RT for 1 mole. So this is called ideal gas equation or perfect gas equation. R value is constant for all gases at all temperatures and pressures. Hence, it is also known as universal gas constant. For two conditions, the ideal gas equation becomes to P1 V1 by T1 equals to P2 V2 by T2. This is known as equation of state. Coming to the next slide. Deviation of real gases from ideal behavior. See, the gas which obeys gas laws, we have already discussed in the previous slides, such as Boyle's law, Avogadro laws and Graham's laws and Dalton's laws, etc. At all ranges of temperature and pressure is called ideal or perfect gases. The gas which does not obey gas laws and general gas equations but tend towards real behavior of low pressure and high temperatures is known as real gas. All gases in nature are real gases and there is no ideal gas in the nature. Thus, the real gas deviates from the ideal gases behavior to some extent or great extent. It purely depends upon the temperature and pressure of the gases. So the next concept is van der Waals equation of states. Gases obey the gas laws at all conditions of temperatures and pressures are called ideal gases. Gases which does not obey the gas laws at all ranges of temperatures and pressures are called real gases. In 1973, van der Waals derived an equation for real gases which follow all conditions of temperature and pressure is known as van der Waals state of equation, or it is also called real gas state equation. It requires some modifications in the kinetic molecular theory of gases. Van der Waals made two correction terms in the ideal gas equation. PV is equal to nRT for applying to real gases. So the two corrections are, the first one is volume correction, the second one is pressure correction. Let's see the volume correction or correction in the volume. According to kinetic molecular theory of gases at low pressure and high temperatures, the volume of container is taken as the volume of the gas. But in case of high pressure, the actual volume occupied by the gas should be taken volume of the gas. Due to this, volume of the real gas is less than that of volume of ideal gas. So therefore, need correction in the volume of the ideal gas. The volume of the gas is the volume of the available for free movement of the molecules. According to van der Waals, the actual free space available inside the vessel for the movement of the molecules is not the volume of the vessel. The available volume is less than the volume of the vessel. So if the V is the volume of the vessel and B is the effective volume of the gas molecule, volume available for the movement of gas molecule will be equal to V minus B. Here B is excluding volume. So it can be corrected volume V minus B. For n moles of gas molecules, corrected volume is V minus Nb, where n is the number of moles of gas molecules. So, after making the correction of the volume, the ideal gas equation becomes P into V minus B equal to RT. So, the next one, pressure correction. According to kinetic molecular theory of gases, there is no intermolecular attractions in between the molecules of gases at very low pressure. But at high pressure, the gas molecules are quite close together and they having intermolecular forces of attractions. Let's explaining with two examples. Consider a molecule A lying in the interior of the vessel. This is attracted by other molecules on all sides and net force of attraction of molecule is 0. When a molecule lying near the wall of the container and the inward molecular dragging back of molecules, so consequently the molecules will strike the wall with lower velocity and will exert a lower pressure. Hence, the actual pressure is less than the ideal pressure. So, it can be expressed as P pressure is equal to P ideal minus PA, where PA is the attractive forces of gas molecules. But attractive forces is directly proportional to the square root of density. So, it can be also written as PA is directly proportional to the density square. So, D is the inversely proportional to volume. It can be expressed as D is equal to 1 by V. That means D is inversely proportional to volume. So, PA is proportional to N by V whole square, where N number of molecules. It can be also written as PA is equal to A into N by V whole square, where A is the proportionality constant or coefficient of attraction. P ideal can be written as P plus PA. So, with respect to the pressure, corrected pressure P is equal to P plus A into N square by V square. Hence, substitute the values of corrected volume and corrected pressure in ideal gas equation, then we get an equation P plus A into N square by V square into V minus NB will be equal to nRT. This is the van der Waal equation for n moles of gas, but for 1 mole of gas the equation is P plus A by V square m into Vm minus B equal to RT. Here small a, small b are called van der Waals constants and their values depends on the nature of the gas and independent of the temperature and pressure. With this, I conclude my session. Thank you very much.